We've said that thermochemistry is the study of energy changes and the gain or release of heat in chemical reactions. But what is heat? Maybe we need to back up a little bit and talk about what heat actually is. Curiosity about heat is not something new. In fact, we know the ancient Greeks were writing about heat and trying to understand what heat was. In the elemental theory of the universe, Empedocles talks about the four elements: earth, air, fire, and water. And of those, earth, air, and water are elemental things. And we know that they're made of multiple elements put together. They're not the fundamental building blocks of living things, but they are matter. The last one, though, fire, is not actually an elemental thing, even though the Greeks considered it to be one of the basic building blocks of the universe. We know now that fire is not actually made of stuff. That wasn't a foregone conclusion for a long time. And in the 15 and 16 and 1700s, as scientists, well, first alchemists and then scientists were working to understand the universe, they were still trying to figure out what fire actually was. One of the first theories, it's really approaching a scientific theory of heat, was Phlogiston Theory, which was really put down on paper by a German alchemist named Becher. He says that this heat that he's getting as he burns stuff, it must actually be an element. Say I have a piece of wood and I burn the piece of wood. The wood is now gone. If I wait at the beginning and at the end, the ashes that are remaining at the end are going to be a lot lighter than the initial log that I started with. So there must have been a loss of mass there. And at the same time, when I burned the wood, I saw these flames licking up, right? These flames, it's super hot. You can roast marshmallows, do whatever. Those flames are obviously something. Well, maybe they're an element. And maybe that phlogiston, which is what he calls it, was trapped in the wood somehow. And then when you burn it and the wood gets smaller, you release the phlogiston. And as the phlogiston escapes, you see it as this fiery stuff. If this was a real thing, you should be able to quantify phlogiston, right? You should be able to measure it. If it's an element like carbon or iron or whatever else, you should be able to measure it. But Becher and Stahl and Pott, which are some of the alchemists / scientists that came later, they had real difficulty measuring phlogiston. And that makes sense because phlogiston isn't actually a thing. It isn't actually an elemental thing. It's energy. The thing that these early phlogiston theory supporters were missing was that as you burn something, you do a combustion reaction, you're producing gases. And the gases are going to escape out into the surrounding area. And when you don't have a sophisticated apparatus to collect those gases and to be able to weigh them and quantify them, it's easy. It makes it look like you just have elements that are disappearing. You make it look like this thing is just getting smaller, when that's not actually the case. The case is that you have energy being released and then gases are being released at the same time. And so if you measure the mass of the thing that you're burning, you measure the oxygen involved. Those are your reactants, right? And your products would be carbon dioxide and water. If you measure all of those things, conservation of mass will hold, and the total mass of the reactants will be equal to the total mass of the products. The scientist who really puts this theory to bed for us in the 1880s is James Joule. We have Joule to really thank for a lot of our early scientific understanding of energy. By the time Joule comes along, phlogiston theory has morphed a bit, and the stuff isn't called phlogiston anymore. They're calling it caloric fluid. And so Joule says, I don't think caloric fluid is a thing. I think that energy is not a material thing. Energy is maybe a property of matter, or energy is something that matter can possess. But energy isn't a type of matter itself. And one of the stories, and we don't really know if it's a true story or not, but one of the stories around Joule and his investigations into matter comes from his honeymoon. And the story goes like this.
Oh, James, 'tis so lovely that we can come here on our honeymoon together.
Oi, my dear, I backed us a lovely picnic under this here waterfall.
Oh, champagne, James, that's so romantic, darling. You know, I was thinking perhaps after this we could go down and take a stroll along the bank. Oh, yes, how about a little Oh, what's that, James? I thought you were going to leave your science kit at home.
Oh, my dear, I do just wonder what's the temperature like of this here yarn waterfall. You doesn't mind, does you?
No, not at all.
It won't just take but a moment, Amelia. Hey, look at this. Temperature's 22 blimey degrees over here. Write that down, Amelia.
James, you promised we would have a nice time. We would not do any science on our honeymoon, right?
Right, Amelia. Okay. Come, let's finish our lunch. I'm done. Promise. You know, I do just wonders what's the temperature like up there at the top of a waterfall.
James.
Oi, it won't take wait a moment here. It's just going quite right up on here. It's just get out a thermometer and say, hey, Melia, it's at 98 degrees. Why, the water's gained energy just by travelling over a waterfall. That's amazing. Energy must be something which can be possessed by matters, not caloric fluid. How could it get any caloric fluid as it went over the waterfall? I always knew that the caloric fluid was malarkey anyways.
And Joule's theory helps us to understand that energy is something that can be possessed by matter, but it's not matter itself. And this is key in establishing the law of conservation of energy. And there are two main types of energy that we're going to be concerned with in chemistry theory. We're concerned with kinetic energy and potential energy. Now remember that kinetic energy is the energy of motion. And if we were looking at kinetic energy in a physics class, we'd be looking at probably the motion of something big, like you could throw a ball or you can drop a textbook, and those objects will have kinetic energy. In chemistry, we're concerned with motion of atoms. So if something has a lot of energy, that means that there is a lot of motion. And the motion can be electrons within atoms moving kind of up to higher and lower energy levels. The energy can be the vibration of atoms connected by chemical bonds, right? As you have a molecule like carbon dioxide, as carbon dioxide absorbs infrared energy from the Earth or from some other source, these bonds are going to stretch like this, so the carbon and the oxygen are going to kind of like wobble back and forth, and they'll also kind of move up and down like this. So the carbon dioxide, if my head's the carbon and my hands are the oxygen, they're going to move like this and they're going to move like this, right? And that's something that has energy. So that carbon dioxide can bump into other molecules and it can transfer energy to those other molecules. And that movement, the rotation or the translation just means move back and forth, kind of like the whole molecule moves this way or the whole molecule moves this way. That's another type of kinetic energy that molecules can possess. So for now we're thinking, okay, if a molecule has a lot of kinetic energy, that means that it's moving. Potential energy is energy which can be converted into types like kinetic. And the main type of potential energy that we're going to look at here is the energy stored in chemical bonds. So if I'm a carbon dioxide molecule, there's also energy stored in these carbon-oxygen bonds here. And we can tell there's energy stored there because if I want to pull these oxygens off, it takes energy to do that. It takes energy to pull a molecule apart. And likewise, when I allow new bonds to form, then energy is released. And so when a chemical reaction happens and you rearrange reactants and products, right? You're pulling reactants apart and you're allowing new products to form. That means that there are going to be energy transfers in that process. This also leads us to a new idea, which is called enthalpy. So the enthalpy of a system is just the total energy that it possesses. So if we take the kinetic energy, the energy of motion, and the potential energy stored in things like the chemical bonds, and we add them together, then what we get is the enthalpy. And the enthalpy is going to be represented by the letter H. Historically, we sometimes called it the heat, but now we're going to call it enthalpy. The enthalpy of a value can't be measured directly, though. Kinetic energy is straightforward to measure for molecules. I can get a sense of the kinetic energy by measuring the temperature of a substance. And the higher the temperature is, that means that I have more kinetic energy. That part is fine, but measuring potential energy is really difficult. Really, the only way I can tell how much energy is stored in a chemical bond is to break the bond and see how much energy did that take, or to allow new bonds to form and see how much energy is given off in the process. All I'm able to measure in Chemistry 30, I can't measure enthalpies directly. But what I can do is I can measure changes in enthalpy. And so we're going to need to use this Greek letter delta. Remember that delta stands for change, and that's what we're going to measure here. So we're not going to measure H's directly, we're going to measure delta H's, or changes in enthalpy. So what the enthalpy change does is it communicates the difference in enthalpy between the products and the reactants. So if I look at the total enthalpy, the total kinetic and potential energy of the products, and I subtract that of the reactants, then I'll get the change in enthalpy between the two things, the delta H. And I can't measure these values directly. So what I do is I take a calorimeter. I'm going to allow a chemical reaction to happen inside the calorimeter. And when I do that, then I'm going to get some change in energy, and that must be equal to the enthalpy change, the products minus the reactants. And I can tell that because if you remember from our calorimetry lesson, you can go back if you need to. If I have my system that I'm trying to measure and the surroundings, and I allow heat to be transferred, if heat is given off by the system, it will enter the surroundings. And if the surroundings are some water in a calorimeter, I can measure the heat gain or the heat loss, the temperature change of the water. And I can use that to figure out how much heat must be lost by the system, gained or lost by the system. So my delta H here, my enthalpy change of the system, will be equal to the heat gained or lost by the calorimeter, right? Because whatever reaction I have happening, say you're burning something like you did in your calorimeter experiment, then the heat that's being given off by that chemical reaction is entering the surroundings, and I can measure the Q. I can measure the energy change of the surroundings. And there are two basic flavors of reactions here, right? I can have an exothermic reaction, I can have an endothermic reaction. So if I want to measure the potential energy, the bond energy of something that's going to do an exothermic reaction, I have some reactants and I have some products. If it's going to end up giving off heat, right? Exothermic means it gives off heat. That means that the reactants must have had more potential energy than the products did in joules, right? We don't care about the numbers right now, but if the reactants must have had more stored energy in their chemical bonds, because when the chemical reaction happened and the reactants turned into products, there was energy that was given off. This is this heat energy that's given off. So if we take products minus reactants, we would see that the enthalpy change here would be negative, right? It would have a negative sign. Anytime I see an enthalpy change with a negative sign, that means that it was an exothermic reaction. In an endothermic reaction, heat is being absorbed by the chemical system. It's coming from the surroundings. So if I study the potential energy over the progress of the reaction, the reactants must have had less potential energy than the products did. Because in order to go from reactants to products, I had to add energy. I had to put heat into this chemical system. And without adding that heat, the chemical reaction is not going to go. These products must have more stored potential energy in their chemical bonds than the reactants did. And so when you take products minus reactants, you'll get a positive value. And anytime you have an enthalpy change that's positive, that means that you had an endothermic reaction. There are lots of different types of enthalpies that we'll calculate. We can calculate enthalpies of just a specified reaction. This is what we'll do a lot of the time. But we'll also sometimes use little subscript letters to specify what type of reaction we're talking about. So if we say, well, we do combustion reactions a lot. So if we do a delta CH, that would be an enthalpy of some combustion reaction. Or a delta FH, a formation reaction. Delta DH, decomposition reaction. Or solution or dilution. So this is when I dissolve something in water, or this is when I dilute something. There'll be enthalpy changes associated with those things too. So if you do see these, you don't need to worry so much about using the letters, but if you see them, it's giving you information about the type of chemical reaction that's taking place. So let's look at an example here. If I have a simple calorimetry experiment, I'm burning a candle under a can of water. This is a really basic calorimeter. We're assuming that the energy from the candle is being transferred to the water. We know it's not a great assumption, but we make lots of not great assumptions in lower level chemistry, and this is just another one of them. We have 100 milliliters of water, so that would be the same as 100 grams. And we have our temperature change here, 16.4 degrees Celsius to 25.2 degrees Celsius. So that means that my temperature has increased by 8.8 degrees Celsius. This substance is also water, which is going to tell us what the specific heat capacity of water is, 4.19 joules per gram degrees Celsius. And we want to know what is the enthalpy change. So what was the enthalpy change of the reaction? Now we said that the enthalpy change is going to be equal to the heat gained or heat lost by the calorimeter, right? This is my surroundings. This is my system. So I know how to calculate Q. Right? Q is equal to MC delta T. So let's figure out what that's going to be. We've got 100 grams of water, 4.19 joules per gram degrees Celsius, and the temperature change was 8.8 degrees Celsius. So then my Q is going to be equal to 3,687.2. This is going to come out in units of joules, right? Because that's the only thing that's left. So for sig digs, let's put this into kilojoules maybe just to make my life a little bit easier. So we get 3 sig digs. Can divide this by 1,000, so that gives us 3.69 kilojoules. Or you could report it as 3.69 times 10 to the power of 3 joules. That's perfectly acceptable too. And here's my Q. Now you notice I'm not quite done because we know that the Q value is going to be the same absolute value as my enthalpy change. So my delta H will have a value of 3.69 kilojoules. But it has to have a sign too. So the enthalpy change here, let's look at the temperature change. Is this an exothermic or an endothermic reaction? If the temperature of the water increases, that means that the candle must have been giving off energy, right? The reaction in the candle was exothermic. It gave off heat. That heat was absorbed by the water. So if the reaction was exothermic, then that means that the enthalpy sign must be negative. And some people will have you do the calculations up here where we actually track signs and have the delta H come out with the correct sign. So they would say delta H is equal to the negative Q, and then you'd have to track your temperature change as being positive or negative. I find that that's a bit of rigmarole. I like to just calculate the value of Q. I know that's going to be the value that my delta H is too, and then I like to just add in the sign at the end based on whether the reaction was exothermic or endothermic. So here's my value. My enthalpy change for this reaction will be negative 3.69 kilojoules, or we could have said negative 3.69 times 10 to the power of 3 joules.